All right, now we'll continue our discussion in this pipe flow problems. Okay, earlier we have discussed the Darcy-Weisbach Weisbach equations, and it's given in the form or mathematically expressed as HL or HF, that depends upon the reference text, FL over D times V squared all over 2G. Okay, so this head loss, this actually referred to as the major loss, right? Major loss. Okay, and therefore, if we have a major loss, then there are also losses that's called minor loss. And the physical interpretation or description is that this major loss refers to the pipe length, the losses along the pipe length. Okay, and that's why we have this L over D. For example, in this illustration, okay, and this one is one of the reference texts by Frank White. And for example, in these situations, we have a reservoir right here and then another reservoir. The flow would be from point 1 to point 2. So we need a pump. So the Darcy-Weisbach equation was actually referring to the losses along the pipe length. So for example, this length of pipe plus the length of pipe, the horizontal length plus this one, the vertical length, and then plus this, plus that. Now another loss also that we need to quantify is the minor loss. Now the minor loss refers to the losses in these valves and fittings and even in the openings. So for example, we have a sharp entrance, then there's gonna be losses in here. Okay, there's gonna be head loss. There's also gonna be head loss in these valves and fittings, these elbows, and then these valves, and then another exits or openings. Okay, so if this is our major loss, then we'll have our minor loss. And the minor loss is sometimes it's just written in terms of HM, which is just simply equal to the summation, right? That's the summation of the coefficients K, summation of K times the velocity head. Okay, so we can now write this as frictional losses. Okay, so we have the major loss and we have the minor loss. Now, even though the name is just minor, sometimes the value of the minor loss can be greater than that of the major loss. Okay, so I think it would be best to describe the minor losses just refers to the losses along, or the losses in the fittings and the valves, whereas the major loss would be the frictional losses along the pipe length. Okay, so this equation, we have the summation of K times the velocity head, where K is called the minor loss coefficient, or some coefficients that can be found in the tables, right? So for example, where can we find this K? And by the way, why is that it's summation? It's simply because you have to sum up, right? You have to sum up all the K values of the, for example, the K values of the globe valve, then the elbow, and then plus the gate valve. Okay, so that's summation of K, then the velocity squared all over 2G. Okay, so one example of this table can be found, actually it is very common in many fluid mechanics textbooks. But this one, Introduction to Hydraulics by Cruz et al. We have this table, it says here values of K sub V for some common hydraulic valves. So for example, we have gate valves, then what's the value of K? That's 0.15. If it's a globe valve, then what's what is the value of K? Then that's 10.0, right? So if it's check valves or rotary valves, and sometimes in other fluid mechanics textbooks, they have also K values for the fittings. Okay, so if it's given in terms of K values, then that's a that's a unitless number. Okay, but sometimes there's also tables that uses equivalent length in pipe diameters. So for example, globe valve fully open, then that's 340. But take note, this is not the K that we've seen a while ago. Okay, so this is the equivalent length in pipe diameters. Okay, so if it's a valve, or right here we have elbows, 90 degrees elbow, 90, straight elbow, long elbow, 45 degrees, okay, close return bend. So we have values for that. Another example of the table is this one. We have this resistance coefficients. Okay, this one is taken from textbook by Frank White. And here we have the resistance coefficients. And it says here we have the nominal diameter in this row. And it says we can have a screwed or a flanged. And here on the first column we have the valves, the elbows, and the T's. Now if the diameter, for example, is 1/2 or 1 or 2, and right here would be the value for the K. Okay, so for example, by the way, when it says screwed or flange, then it means that, for example, this is our elbow, or let's just draw flange. Okay, so for the flange, I mean valves. So if these are our valve, then it is possible that a valve can be screwed. So if it's screwed, then there must be some threads right here. Okay, so let's say this is our valve. Now if it's flange, then the construction of the valve would be something like this. Okay, so there's a flange right here. So of course, if it's a flange, then you have to connect also pipe with flange, and then you have to provide a bolt right here in order to join the pipe and the valves. This is screw, then of course you have to mate that with a threaded pipe. Okay, so we have the diameter and we have the valves and fittings right here. So we can solve for the K. Alright, now let's do one more problem regarding this pipe flow problem. So this problem is taken from the textbook of White, and that's example 6.16. Okay, so the problem says water is pumped between two reservoirs at 0.2 feet cube per second through 400 feet of 2 inches diameter pipe and several minor losses as shown. The roughness ratio is 0.001, and take note, this ratio is the epsilon divided by D, and when we use the textbook by Mott and Antenna, it's I think that's the other way around. It's the D over the epsilon. Okay, so the problem says compute the pump horsepower required. Okay, so for the solution, we have to first establish the energy equation. Okay, and in this problem actually we have to take into account the presence of the minor losses. Okay, so first one, let's establish the energy equation. So that's P1 by the unit weight plus the elevation. Okay, so the elevation is given, the Z1 is 20 feet, Z2 is 120 feet. Okay, Z1 plus the velocity head, 2g, right, plus that's the energy in is equal to energy out. So plus the energy provided by the pump, so that's HA, is equal to the pressure head at point 2 plus elevation head plus velocity head at point 2, right, plus, right, since we don't have any fluid motor or turbines, then we can just neglect the term, but we have the H sub L. And then since we also have minor losses, we have to include the minor losses, then we can just write a separate term, H sub M. Okay, so simplifying, we get, since this is a large reservoir, then this one would be 0, this one would be 0, and of course the velocity head at point 1 would also be 0, right, because this is a large reservoir. So the assumption is that if this area is way larger than the area right here, I mean along the pipes, then we can just assume that the velocity would be 0. Okay, and this one, since this is also a large reservoir, then this one would also be 0. Therefore, our remaining terms would be Z1 plus H sub A is equal to Z2 plus H sub L plus the minor loss. Therefore, if we want to find the head provided by the pump, then that's H sub A is equal to Z2 minus Z1, the difference in the elevation, plus the head loss, right? That's the major head loss plus the minor head loss. Okay, so right, the next step now is to solve for the velocity. We need velocity simply because in this headless equation we need the v squared over 2g. Also right here we need the v squared all over 2g. So that's the velocity along this pipeline. Okay, so we're not actually given directly the velocity, but we have the flow rate plus we have this diameter, 2 inches diameter. Okay, so that's going to be the flow rate equation. Q is equal to AV, and therefore velocity is just simply Q all over A, and our Q is 0.2 feet cubed per second, and our A would just be simply equal to, of course this is 2 inches, then you have to convert that to feet. So this is pi times 2 divided by 12, right? That's 12 inches in 1 foot. Right, so inch, then pi d squared all over 4, and our velocity would be 9.17 feet per second. Okay, now let's solve for or we'll use another paper. That's number 3, solve for H sub L. Now, however, if we want to solve for H sub L, we want to solve first for the Reynolds number, which is the velocity times the L sub C, characteristic length, which is just simply the diameter, and times the, okay, we'll just use the nu, kinematic viscosity. Okay, and this one, the velocity is 9.17 feet per second, right, times the characteristic length of that's 2 all over 12 divided by this, which can be obtained from the tables, 0.0011. and we have a value of 139,000. 139,000. Therefore, if we know the Reynolds number, then we can go to the Moody chart. Okay, go to the Moody chart to find F, and the F value is equal to also to find F, but however we need to use the roughness, okay, at this relative roughness E over D is equal to 0.001. Okay, so therefore F is equal to 0.0216. Now once you have the F, then you can solve for the H sub L, which is F L over D times V squared L over 2G, right? 0.0216 times the total length. The total length is 400 feet. That's 400 divided by 2 inches divided by 12 to convert that into feet, times the velocity, which is 9.17 squared all over 2 times G. However, since we are using the, or we are solving using the English units, then this one should be 32.2 feet per second squared. Okay, and if we do the computation regarding this, what we get is, right, 9.17 squared divided by 2 times 32.2, right, times 400 times 0.0216 divided by 2 all over 12. So that's 67.69 is what should be in feet. Okay, so now we have the major loss. Then let's move on to solve for the minor loss, H sub M. Now the H sub M is just simply equal to the summation of K times the V squared all over 2G. Okay, so now let's list down our I think it would be best if we present this one in terms of tables. Okay, so let's write. First we have a sharp entrance. So we have sharp entrance, and our next one is the open globe valve. Now, open globe valve. And then the third one, okay, so the third one would be this, the 12-inch bend radius. So 12-inch bend radius. Then the next one would be the screwed regular 90 degrees elbow. Screwed regular 90 degrees elbow. And then after that we have a half closed that's half closed gate valve, or half open, right? Half closed or half open, half closed gate valve. And the last one would be the sharp exit, right? So sharp exit. Okay, so what are the K values of these valves and fittings? Okay, so now let's go to this table. And by the way, since the problem is taken from this textbook, then that's the reason why I decided to use the tables provided in this textbook instead of using our own lecture handouts. Okay, so we are it says here we have your screwed regular elbow, right? Screwed regular elbow. So we are here screwed, and then the nominal diameter of the pipe is 2 inches, Therefore, let's check the values of, okay, it says here open globe valve. So for example, open globe valve, we have the 2 inches, and this is the globe valve fully open, and it says here we have a 6.9 values, right? 6.9 values. And for 90 degrees elbow, for example, 90 degrees regular elbow, that's 0.95. And others, if it's not, obtainable directly from the table, then you can do interpolations, or you can refer to other tables which will have probably slightly different values. Okay, but anyways, in summary, what we'll have here is 0.5, this one is 6.9, this is 0.25, this is 0.95, and the half closed valve, this is 2.7, and this is 1.0. By the way, some of these minor losses, they are actually obtained using equations, like for example, I guess the sharp entrance and the sharp exit. However, if I did not discuss it anymore, but the main idea is that for the valves and fittings, for the minor losses, you can just refer to the textbooks, and there are a lot of tables available. Okay, so you sum this up, because what we need in the equation is the summation of k, right? So summation of k, we get 12.3, and therefore a sub m is equal to 12.3 times the v squared, which is 9.17 squared, right, all over 2g times 32.2. So if we do the computation, we have 9.17 squared times 12.3 divided by 2 times 32.2, and we get a value of 16. That's 16 feet, and therefore for our equation, we have h sub a is equal to z sub 2 minus z sub 1 plus h sub l plus h sub m, and the difference in the elevations is just 120 minus 20, and they're both in feet. This one, h sub l, is 67.69 plus the minor loss, which is 16 feet. Therefore, this is 100 plus 67.69 plus 16, and we have a value of 183.69, or 184 feet of pump head. Therefore, to find, we have here, compute the pump horsepower required. Now, although we haven't we didn't include this equation in our lecture handouts for this topic, the equation for solving the HP of, let's say, the horsepower of pump, is just equal to the unit weight of the fluid times the flow rate times the head of the pump, or the H sub A. And if we have water, then this one is 1.94 times 32.2. This is I think this is slugs per feet cube, and then times the gravitational acceleration. Then we multiply that to our flow rate, which is 0.2 feet cube per second, and then our pump head of 184 feet, and what we get is 2,300 foot-pound per second. But the conversion of foot-pound per second to HP is that 1 HP is equal to 550 foot-pound per second, and therefore this will be 2,300 pound per second, right, times 1 HP divided by 550 foot-pound. Therefore, what we get is 4.2 HP, right? Okay, so in summary, if we have to include the minor loss, then we just have to include another term right here in the energy equation. And sometimes you can actually express this. I think you can also do this since this is FL over D times the velocity head, V squared all over 2G, and this one is simply summation of K times V squared all over 2G. Then you have this common term right here, and you can just factor out this one. And so what's left will be FL over D plus the summation of K, since they're both dimensionless, right, times the velocity head, V squared all over 2G. Okay, so you can do that as well if you'd like. All right, now that's all for our topic in this internal flows. And next, in the next topic, topic number 9, we will be discussing the multiple pipe system. So what will happen if the pipe is in series or the pipe is in parallel? So we have to do some computations regarding that as well. All right, so see you in the next videos.